In the previous lecture, we showed the existence of a splitting field. Let me quickly recall what it is. Starting with a field f and the polynomial with coefficients in f, a non-constant polynomial with coefficients in f, we can always find some extension of the field f that contains all the zeros of the polynomial f. Or alternatively, I can say that we can find some field extension of the field capital F where we can write down the polynomial f as a product of degree 1 factors. If we take the smallest such field, if we take a smallest such field, we call it a splitting field of this polynomial. So field E is called a splitting field of the polynomial f over the base field capital F if E over F is E is a field extension of F, and the polynomial small f can be written as its leading coefficient times the product of these degree 1 factors, x1, x minus alpha 1, dot x minus alpha n, where alpha i's belong to this field extension, and moreover, the field extension is generated by the field f and these alpha i's as a ring. So again, alternatively, this means E is the smallest ring that is generated by f and alpha i's as a subring of E. So every element of E can be realized as a multivariable polynomial evaluated at alpha i's. Okay, so if we have such a field, we call it a splitting field of the polynomial f, and in the previous lecture we showed existence of such a field extension. And then we started working towards the uniqueness of such a field extension. Of course, when we say uniqueness, we mean up to an isomorphism. If you remember, the way that we proved existence of such a polynomial, such a field extension was first by considering an irreducible polynomial and showing that we can always find some field extension that contains a single zero of this polynomial. And then we proceeded by a strong induction in order to add other zeros of a given polynomial to the original field. Now, we want to proceed by the same kind of mechanism, strong induction, to show the uniqueness of a splitting field up to an isomorphism. So in order to be able to do this process, we need to actually show a stronger statement. And we showed certain statement, meaning starting with an irreducible element, what happens after we add a zero. And we said, okay, let's start with 2 copies of a single field f, and I give you an irreducible polynomial, and I add a zero of the first polynomial in the first copy, and a zero of the same polynomial but in the next copy. And then we ask ourselves, what do we get after we add these zeros? And we showed that we get an isomorphic fields, and in fact we get an isomorphism that's an extension of the original isomorphism. Okay, let me again remind you the formulation of the statement. So suppose that we are given an isomorphism between 2 fields, f and f prime. So that's what I mean by having 2 copies of the same field. And we are given a polynomial, small f, with coefficients inside the first copy, capital F, and we are told that it is irreducible. It's time for that. We are told that it is irreducible. Now what we want to do, we want to add a zero of f to capital F, and we want to add a zero of theta of f, the next copy, the copy of this polynomial in f prime to f prime. And we are wondering what is, if there is a connection between these new fields. So again, E is a field extension of f that contains a zero of the polynomial f, this irreducible polynomial, and E prime is a field extension of f prime, which contains a zero, let's call it alpha prime, of, so here it should be prime, a zero of theta of f, the copy of f with coefficients inside f prime. Then, in that case, we can find some isomorphism between f bracket alpha and f prime bracket alpha prime. And this isomorphism, when I restrict it to f, to this part of this ring, to f, I will end up getting the same isomorphism as before. So the f portion goes to f prime portion, and it's done through the isomorphism theta, and alpha is sent to alpha prime. So altogether, I can say that an element like this, so I can write it like this. Let's write it with red, let's say. So theta hat of a polynomial evaluated at alpha, something like this, is the copy of this polynomial through theta evaluated at alpha prime. And what we are saying is that such a theta hat is well defined, and it is indeed an isomorphism between f bracket alpha and f prime bracket alpha prime. So this is the claim that we proved in the previous lecture. Okay, so let's see an immediate corollary of this statement when f is in fact f prime and theta is nothing but identity. So in that case, still we get something non-trivial, and let's call this corollary. So suppose that we are given a field extension of f, and we are given an irreducible polynomial with coefficients inside f. And in this field extension, we have two elements, alpha and alpha prime. Both of them are zeros of this irreducible polynomial. In that case, we can find a ring isomorphism, let's call it theta hat, from f bracket alpha to f bracket alpha prime, where whatever polynomial I give you when it's evaluated at alpha, this theta hat sends it to the evaluation of the same polynomial at alpha prime. If you remember, I mean, we have seen this type of isomorphism when we were working with the zeros of quadratic equations, and in that case, we call such a thing conjugation. This is in fact identical to complex conjugation when we are dealing with the equation x squared plus 1. So in the case of x squared plus 1 as a polynomial with real coefficient, with real coefficients, we know that here this is irreducible because it's a degree 2 polynomial with no real zeros. And there are two solutions for this in complex numbers. One of them is I, the other one is negative I. And the map that sends any polynomial evaluated, any real polynomial evaluated at I, when we send it to g of the other root, which is negative I, this is nothing but complex conjugation. It's precisely complex conjugation. And what we are saying here is that complex conjugation preserves addition and multiplication, and it's a bijection. So earlier when we were discussing norms and we wanted to understand irreducible elements inside certain ring extensions of integers, ring of integers, after adding a zero of a quadratic equation, we use this type of maps for two zeros of a quadratic equation and sending one zero to the other one. In any case, now we have this general kind of statement that whenever I give you a single irreducible element, irreducible polynomial, then I can always send one of the zeros of this polynomial to another one and gain a ring isomorphism between f bracket alpha to f bracket alpha prime. This type of statement is going to play an important role in Galois theory when we want to understand the so-called Galois groups and so on. And so this type of a statement is actually very important. So later on, when we discuss the action of Galois group on the set of zeros, we say that this statement actually implies that the action is so-called transitive. I will define these things later on. But what I'm saying is I want to emphasize the importance of this corollary. Okay, so how does the proof go? The proof is an immediate corollary, an immediate consequence of the result, the lemma that we proved in the previous lecture. So theta from F to F is so we take it to be the identity map. Then by the lemma that we proved in the previous lecture, we do know that there exists some ring isomorphism between f bracket alpha and f bracket alpha prime, such that when I restrict it to f, I end up getting theta. That means when I restrict it to f, I get the identity function, and moreover, we know that this theta had this property that theta hat of alpha is alpha prime, which means for every polynomial g with coefficients inside f, when I evaluate it at alpha and ask myself what happens when I apply theta hat, first I use the fact that theta hat is a ring homomorphism and write this as summation of theta hat of the coefficients times theta hat of alpha to power I. But theta hat of alpha is alpha prime, so I get alpha prime to power I, and theta hat of Ci is an element of the field F. And I know when I restrict theta hat to the field F, I get the identity. So I'm not changing elements of the field F, in particular theta hat of Ci is Ci. And what I'm getting is the polynomial G evaluated at alpha prime. So altogether, we are getting that whenever I give you two zeros of an irreducible polynomial with coefficients inside a field F, there is an isomorphism between f bracket alpha and f bracket alpha prime, where we send alpha to alpha prime, and it is linear with respect to f. So that means theta hat of every element of the field F is the same. So theta hat of C is C for every C inside this field. Okay, so now we are prepared in order to, in fact, prove a stronger statement than saying splitting fields are isomorphic to each other. So a splitting field is unique. We are going to prove slightly stronger statement, but this stronger version actually can help us to go through the induction argument in an easier fashion. That's first thing. And second, again, it will help us later on when we want to understand Galois extensions. So again, this is an important theorem, not only because it shows us that splitting fields are unique up to isomorphism, but also it will help us to understand, classify, distinguish Galois extensions from the rest of extensions. So we will talk about them later on, of course, but I want to emphasize the importance of this theorem. Okay, what is the statement? The statement is I'm giving you two fields. They are the same fields, but different copies of the same field, which means I'm giving you two fields, f and f prime, and an isomorphism between them. So essentially they are the same fields, but different copies. And I give you a polynomial, in a non-constant polynomial with coefficients in the first copy. So small f is a polynomial which is not constant with coefficients inside the field capital F. Now, suppose I give you a splitting field of this polynomial over F. Okay, so E is a splitting field of the polynomial F over the field capital F. Now, I give you a splitting field of the copy of this polynomial in F prime, which means I'm assuming that E prime now this time is a splitting field of the polynomial theta of F over F prime. So E is a splitting field of F over capital F, and E prime is a splitting of theta of F over F prime. In that case, E and E prime are isomorphic, and the isomorphism is compatible with the isomorphism between F and F prime. What does compatible mean? It means that when I feed it, so there exists this theta hat, an isomorphism between E, the splitting field in the first copy, and E prime, the splitting field in the second copy, such that for every element of the smaller field F, when I feed it to theta hat, what it does to it is precisely what theta did. We again can capture this in this commuting diagram or commutative diagram. So what does that mean? This means given two fields F and F prime and an isomorphism between them, so F sits inside E and F prime sits inside E prime. So E prime is a field extension, is a splitting field of this polynomial. So it has a copy of F prime in it, and E has a copy of F in it. And we are given this picture. In that case, we can complete the square, complete it, and put a theta hat, the arrow theta hat at top, so that the whole thing is compatible. And that means that I should be able to go from here to there, and then go up, which means I get back theta of C. And that should be the same as going up, which means getting to C, and then applying theta hat. And that's exactly the equality that we have written over here. So we can write it in this pictorial way by saying that this diagram is a commutative diagram. Okay, so let's see how we can prove this a uniqueness statement. It's a rather strong uniqueness statement. Okay, so similar to the existence part, we are going to proceed by induction on the degree of the polynomial f. If the degree of my polynomial is 1, the base of induction, then it means the polynomial f looks like ax plus b, which means, and a is a non-zero constant inside f, which means that my polynomial looks like this, and this element is in f. And that's the only zero of this polynomial. So altogether, this observation implies that f is the only splitting field of this polynomial of degree 1 over f, because I don't need to add anything to f. The zero of this polynomial of degree 1 is already inside the field capital F. Now, because f is of degree 1, theta of f is of degree 1, and therefore the splitting field of theta of f is again E prime, or F prime rather. So which means I can take theta hat to be just theta, because E is F. Oops, because E is F, and E prime is F prime. So we can choose theta hat to be just theta, and that satisfies the claim that we had. So that gives us the base of induction. Now I'm going to discuss the induction step. I should warn you that the induction step is a bit technical, but the main idea is actually rather easy. So first I'm going to show you the technical part. We go through all the details, but then at the end I'm going to summarize it and mention the important parts of the argument. Okay, so what is it again? We start by asking ourselves, what does it mean that E is a splitting field of this binomial f? And what does it mean that E prime is a splitting field of theta of f? When we say E is a splitting field of f, that means over E, we can write down f as a product of degree 1 factors. So I can find some alpha 1, alpha 2, alpha n inside this larger field E in a way that the binomial f is, of course, its leading coefficient times these product of degree 1 factors. Moreover, this field E as a ring is generated by f and alpha i's, which means that if I consider the smallest subring of E that contains f and alpha i's, I end up getting the entire ring E. So E is generated by the field f and zeros of this binomial. Now, similarly, when we say E prime is a splitting field of the binomial theta of f, that means we can find some zeros inside E prime and write down theta of f as its leading coefficient times product of these degree 1 factors. And E prime is the smallest ring that contains f prime and these zeros. So that's the meaning of splitting field. Again, one observation that we have to make, we can make is that when I apply theta to a binomial, it's like applying it to the leading coefficient as well. So the leading coefficient of theta of f is nothing but theta applied to the leading coefficient of f. Leading coefficient of f be denoted by a, and leading coefficient of theta of f be denoted by a prime. So a prime is nothing but theta of f. This is an observation. It's not very important, but it's good to know. Now, what we want to do, you see, at the end of the day, we have theta, and theta only applies to the elements of f. But these alpha i's are not inside f. So what we want to do, we want to take a part or some irreducible factor of the polynomial f, irreducible inside f bracket x. You want to take that guy out. So one way of doing it to make it kind of compatible with the roots zeros of the polynomial f is by taking the minimal polynomial of alpha 1. So we choose one of the zeros, let's call it alpha 1, and then we do know that it's an algebraic element because it's 0 of the polynomial f, and that means the minimal polynomial of alpha 1 over the field capital F is irreducible, is an irreducible factor. It's irreducible and it divides the polynomial f. It divides the polynomial f because alpha 1 is a 0 of this polynomial. So it's an irreducible factor of the polynomial f of x. Now, because theta is an isomorphism from f bracket x to f prime bracket x, we deduce that theta of this minimal polynomial is an irreducible factor of theta of f. Now, over E prime, theta of f can be written as product of degree 1 factors x minus alpha I primes. Theta of this minimal polynomial is supposed to be a divisor of theta of f. That means by using the fact that ring of binomials is a UFD, we can write down the theta of this minimal binomial as product of sum of the irreducible factors of theta of f, which means some of these degree 1 factors. Again, these degree 1 factors are irreducible elements of E prime x, and E prime x is a unique factorization domain. So knowing that theta of this minimal binomial divides this product of irreducible elements, and it's a monic binomial, it should be a subproduct of them. So that means I can find some indices and write down theta of this minimal binomial as x alpha sub I I1 prime and times x minus alpha sub I2 prime and so on. Now I can rearrange the order of alpha sub ij's and assume that the smallest one is alpha 1 prime. So I can change, let's say, I sub 1, the indexing, and make it to be alpha 1 prime. So without loss of generality, we can and will assume that x minus alpha 1 prime is a factor of theta of this minimal binomial, which is equivalent to saying that alpha 1 prime is a zero of this binomial. Okay, so far so good. Let's summarize what we have done. So far, we found an irreducible element in f bracket x, which is a divisor of f, and then we apply theta to this, and that is again an irreducible element, but this time in the next copy, f prime, and it contains a zero of theta of f, so it has a common zero with that one, and we call that alpha 1 prime. Now, because this is an irreducible element inside f bracket x, and this is another copy of this irreducible element, alpha 1 was a zero of this irreducible binomial, and alpha 1 prime is a zero of the other copy of this binomial. By the result that we proved in the previous lecture, we get an ring isomorphism between these fields f bracket alpha 1 and f prime bracket alpha 1 prime in a way that is compatible with the isomorphism that we had between f and f prime, and it sends alpha 1 to alpha 1 prime. Okay, so its restriction to f is just the theta that we had, and it sends alpha 1 to alpha 1 prime. Okay, so now what? Because alpha 1 is a zero of this polynomial f, by factor theorem, I can write down f as x minus alpha 1 times some polynomial with coefficients inside this larger field. So after adding alpha 1 to f. And we already know that f can be decomposed completely as product of degree 1 factors in this larger field E. Now equality, if I set these guys equal, I deduce that this factor g is a times product of these degree 1 factors. But this time starting from alpha 2, x minus alpha 2 dot dot x minus alpha n. Now when I apply, you see, remember this theta 1 was an isomorphism between the fields f bracket alpha 1 and f prime bracket alpha 1 prime, and we can always extend such an isomorphism to an isomorphism between ring of binomials. So I can apply this isomorphism to both sides of this equality. And I end up getting that, so in fact, this equality, sorry for that. So applying that theta 1 hat to both sides of this equality, we get that theta 1 hat applied to f is the same as theta 1 hat applied to the first parentheses to this linear factor, which is x minus theta 1 hat applied to alpha 1 times theta 1 hat applied to g. But remember, theta 1 hat restricted to the field capital F was the same as theta. And f, the polynomial f, belongs to this smaller field. Therefore, theta 1 hat is nothing but theta. So we get the equality that this is the same as theta of f. And theta of f, we assume that is equal to a prime times the product of these degree 1 factors. On the other hand, we also know that theta 1 hat sends alpha 1 to alpha 1 prime. So we get this equality, and I can cancel out x minus alpha 1 prime from both sides. And I end up getting that the image of this auxiliary polynomial of a smaller degree, g, the image of this completely splits into degree 1 factors after adding the root alpha 1 prime to the base field f prime. Okay, so let's look at these equations carefully. So we want to use strong induction hypothesis and apply it to the polynomial g. That means I need to get a better understanding of the splitting field of the polynomial g. Notice the polynomial g has coefficients inside this slightly larger field. So when we say splitting field, this means we have to start with this base field, which means a starting field, and then add the other zeros or all the zeros of this polynomial g. So again, that means I'm starting with this base field f bracket alpha 1, and then I'm adding all the zeros of g. But by looking at this equality, as you can see over here, zeros of g means alpha 2, alpha 3, alpha n. So this means I need to add alpha 2, alpha 3, alpha n to this base field. So altogether, I'm adding alpha 1, alpha 2, alpha n to the field f. In this case, I get the ring E back because E was generated by f and alpha i's. So this means E is a splitting field of this smaller degree polynomial, but over this larger field f bracket alpha 1. By a similar kind of argument and using this time this equality, this time I have to add alpha 2 prime, alpha n prime, these are zeros of theta 1 hat of g. I have to add them to the base field f prime bracket alpha 1 prime. And by adding them, I get the splitting field of this polynomial. But what do I get really? I get f prime added to alpha 1 prime. Then I add the other zeros. So altogether, it's like adding alpha 1 prime, alpha 2 prime to alpha n prime to f prime, which means I'm getting back E prime. So E prime is a splitting field of theta 1 hat of g over the base field f prime of alpha 1 prime. Now that we are in this position that E and E prime, both of them are a splitting field, but this time splitting field of a smaller degree polynomial, we can use induction hypothesis and obtain a ring isomorphism between these fields, E and E prime. We can find such a ring isomorphism that its restriction to f bracket alpha 1 is this theta 1 hat that we have. So again, let's summarize what we had so far. So we started this alpha 1, we looked at the minimal binomial, we applied theta, we said that it should be an irreducible factor of theta of f. So one of the zeros should be a zero of this binomial as well. Without lots of generality, we assume that that one is alpha 1 prime. And because these are irreducible binomials from the result that we proved in the previous lecture, we can find a ring isomorphism between f bracket alpha 1 and f prime bracket alpha 1 prime. And this ring isomorphism sends alpha 1 to alpha 1 prime, and its restriction to f is the same as theta. We also argued that E is a splitting field of this auxiliary polynomial G over this larger field. And similarly for E prime, we realized it as a splitting field of a smaller degree polynomial. So because the degree is strictly less than the degree of the field in the polynomial f, we are allowed to use the induction hypothesis. So using the induction hypothesis, we find this field isomorphism or ring isomorphism between the fields E and E prime, such that the restriction to this intermediate field f bracket alpha 1 is the theta 1 half that we have. So altogether, the whole thing is like this, that we start with this isomorphism between f and f prime. We add only one of the zeros of the first one, and then we say, let's look at the minimal binomial of this alpha 1, apply theta to that, take one of the zeros of the image of this minimal binomial, call that guy alpha 1 prime. Then we can find some ring isomorphism between these two fields that sends alpha 1 to alpha 1 prime, and its restriction to f is like theta. So that means this diagram is a commutative diagram. Next, we use strong induction hypothesis and view E as a splitting field of a smaller degree polynomial, view E prime as a splitting field of a smaller degree polynomial, and use the strong induction hypothesis to complete this square and obtain theta hat. And because all the pieces of this diagram are commute, we end up getting a commutative diagram. And that's exactly what we wanted to show. So again, now let's go through the, as I have promised, let's go through the ideas of the proof. The idea is rather easy, but the steps are a bit complicated. They seem to be complicated, many variables and so on. But the ideas are, again, simple. What are the ideas? First, we take an irreducible factor of this polynomial f. Let's call it h. Then we take a zero of this irreducible factor, and we take a zero of the copy of this irreducible factor inside f prime. Then we can find a ring isomorphism between the rings that we get after adding the zero of the first copy and a zero of the next copy. Now we take this isomorphism as an intermediate isomorphism, and what we do is we view E as a splitting field of a smaller degree polynomial, and then we can use induction hypothesis and go through this diagram and finish the proof by induction. Okay, so an immediate corollary of this uniqueness result that we are proving, it's a very strong uniqueness result, is the fact that the splitting fields are in fact isomorphic. If I pick, again, if I start with a field f and a polynomial small f, if I give you two splitting fields of this polynomial, then there exists a ring isomorphism between these splitting fields such that over F I just get identity. I don't change. So alternatively, I can say that theta hat is an F linear map. When we discuss linear algebra over fields a bit more in details later, this phrasing makes more sense. This is an immediate corollary of the previous uniqueness result that we proved. In fact, this is just applying that to the identity map from F to F. So there are no two copies of the same field. It's the same field F, and I'm taking identity from F to F. And then in that case, we get this theta hat that's an isomorphism between the splitting field of the binomial F in first copy and second copy, but they are the same binomials. So we get exactly this statement. So in general, splitting fields are not that easy to compute. But let's see a few examples, a couple of examples on how we can compute or understand or write down concretely what the splitting fields are in certain examples. So for instance, one example is the binomial x to the n minus 1, and this time we want to understand its splitting field over the base field q. And the claim is that this splitting field can be generated by a single element, and that is the nth root of unity zeta sub n. So zeta sub n is e to power 2 pi in. It is this is one of the nth roots of unity. If you remember from complex analysis, what happened here? Okay, I have to do this one maybe, and then I do this, and then I draw it like this, and then I say that we have 1 and then nth roots of unity over the unit circle, complex multiplication. It's like rotation, and what we are doing is when I multiply it by itself, it goes like that. After n step, I get to 1, and that is 1. That is why we have 2 pi over n. Remember, e to power I theta is like rotation by angle theta. Okay, so so that is the claim. Let's try to understand what's going on. In order to understand the splitting field of a binomial, we need to split it completely over a larger field. Here we are going to make use of complex numbers, and I'm going to split x to the n minus 1. I'm going to factor it into linear factors, but over complex numbers. In order to make it a bit more systematic, what we do, we start with zeta sub n. We observe that zeta sub n to power n is identity. That's in fact how we define zeta sub n. And from here, one can immediately deduce that the same statement is true when I raise zeta sub n to power j. So zeta sub n to power j raised to power n, it's like 1 to power j, is again 1. And these are distinct zeros of the binomial x to the n minus 1 if I just consider the powers that are in the range 0 to n minus 1. So in that case, that means 1 zeta sub n to power n minus 1 are distinct zeros of this degree n polynomial. Now, by the generalized factor theorem, whenever I give you distinct zeros, you can factor it out as product of degree 1 factors. Now I notice that there are n of them, and x to the n minus 1 has degree n. So this means that x to the n minus 1 is essentially product of these degree 1 factors. And I say essentially, this means in principle, I need to multiply by the leading coefficient. But here, it's a monic binomial. The leading coefficient is 1. So altogether, I end up getting the x to the n minus 1 is x minus 1, x minus zeta sub n, dot x minus zeta sub n to power n minus 1. We get this linear factorization. Therefore, by the definition of a splitting field, if I call E to be the smallest subfield of complex numbers that contains Q and zeros of this binomial, which means 1, zeta sub n to power n minus 1, this subfield would be a splitting field of the polynomial x to the n minus 1 over the field Q. Now, one thing that we can observe immediately is that zeta sub n is among these elements, and therefore Q bracket zeta sub n is definitely a subset of this smallest field that contains all these powers of zeta sub n. Now, when we say it out loud, we clearly see that the powers of zeta sub n, they are already inside this ring. So that means for every j, we already have that this guy belongs to Q bracket zeta sub n, but these guys are supposed to generate the subfield E. So that means immediately we get that E is a subfield of Q bracket zeta sub n. So altogether we get equality. That's exactly the claim that we were looking for. So a splitting field of x to the n minus 1 over Q is nothing but adding the nth root of unity to Q. Let's do another example. What is the splitting field of x to the n minus 2 over Q? This is also an important example later on when we want to understand Kummer theory and radical extensions. We come back to this type of example. So when I say later on, I don't mean necessarily in this course. We continue in 100C, the study of Galois theory and Kummer theory and so on. So x to the n minus 2, we want to understand its linear factors over complex numbers. Again, we notice that when I take zeta sub n raised to power j, multiplied by the nth root of 2, and raise the entire thing to power n, then the zeta sub n part will be 1. So we end up getting that the whole thing is 2, which means we end up showing that the nth root of 2, zeta sub n times nth root of 2, zeta sub n to any power times nth root of 2, all of them are zeros of x to the n minus 2. Again, we have n distinct zeros. X to the n minus 2 is a monic binomial. So by a combination of the generalized factor theorem, comparing degrees and leading coefficients, we obtain that x to the n minus 2 is the product of x minus the nth root of 2, x minus zeta sub n times nth root of 2, and so on. So that means if I look at the smallest subfield of complex numbers that contains Q and zeros of this binomial, which means the nth root of 2, zeta sub n times nth root of 2, and so on, then this E is a splitting field of this binomial x to the n minus 2 over Q. Now, because the nth root of 2 and zeta sub n times nth root of 2 are supposed to be inside this field, their fraction, their ratio should be inside this field. That means the nth root of 2 and the nth root of unity should be inside E. The nth root of 2 should be inside E because of this. Now we deduce that the nth root of unity should be inside E. So Q bracket nth root of 2 and nth root of unity, both of them should be inside E. Now, if I have these two inside E, I immediately deduce that these products are inside E. Altogether, we deduce that E is precisely the ring generated by the nth root of 2 and the nth root of unity and Q. So we get this equality. So in the next lecture, we are going to use splitting fields to study finite fields. For now.